Hello everyone, welcome to today's tutorial. In this video, we are going to explore the concept of the high-performance liquid chromatography, the Van Deemter's equation, and the factor that affects the column efficiency or the column efficiency parameter. Don't forget to like and subscribe after watching the video so that you can receive every bit of updates that we drop on this channel. So basically, this is the basic setup or the chromatograph of high-performance liquid chromatography. It ranges from the first parts, which is a solvent reservoir. So the solvent reservoir, this one is what accommodates the solvent or the mobile phase that you are going to use to run your experiment. The next one is what you call the pump. So the pump here is just the component that more of sucks the solvent or the mobile phase from the reservoir and transfer it through this direction arrow to the column. So we have first one, the solvent reservoir, that accommodates the mobile phase or the solvent that you're going to use for your HPLC analysis. Then the second one is the pump. The pump more like sucks or delivers the solvent from the reservoir to the column. Then we have the third component we call the sample chamber or the injector. So this part shown double here, this part is what basically introduces the sample into the column. So let's say if we have the sample in this beaker, the injector is being introduced to this part of the HPLC, and the coming solvent, which is sucked from the reservoir by the pump, is being transferred to the HPLC column. So the column, this is the column. What the sample reservoir does is it adds the sample this particular part of the setup. Then the pump now sucks the solvent from the reservoir, and the solvent coming here transfers the sample, which is being introduced here through what we call injection, to the column. So the process of adding the sample to the system is what we call the injection. Now when the sample is being injected, the solvent now runs and moves this sample to this particular arrow or direction arrow to the column. Now in the column is where we have the packing material. So the silica gel for a normal phase HPLC, or let's say carbon 18 for a reverse phase, is what is packed in the column. So in the column here, here's where the separation occurs. So when the samples reaches the column system or the front of the column here, the separation now continues, and as they move down the column, the separation is now going to be based on the affinity, so being the polarity for the differences in their adsorption capacities to the silica or the packing material. When they run through, they are going to be separated as bands in the column, and the band is basically due to the fact that the samples or the mixed components of the sample have different affinities for the packing material. Now when the samples exit the column, which is at the end here, we call the ejection. The samples now pass to the detector. So the detector is what detects the properties of the sample and displays the properties that it receives as what the chromatogram, which is shown on the computer screen. So the sample that reaches the detector is being detected and is being shown as a signal. So this signal is called for the chromatogram that gives a particular property or is based on the properties of the sample. The detectors comes in different forms. We can have what we call the UV detector, which is basically used to detect the conjugation properties of the compound. We can have the refractive index detector, which basically detects the ability of the sample to reflect or to refract a particular light. We can have what we call the mass spectrometer detector, which basically displays the property based on the molecular weight of the sample. Then we have other detectors. So what is displayed on the screen here is basically based on the detector's property, being it UV detector, let's say refractometer, a mass spectrometer, or even you can have what you call an electrochemical detector, or maybe fluorescent detector. So all these detectors display different property of the sample on the screen. Now, what is displayed on the screen here is called the chromatogram, and it's basically the display of the detector's property against the retention time. So the diagram shown here, this is what is displayed basically on the computer screen after detection. So this diagram, the chromatogram, is, we can say this, let's say a plot of the detector's property against the retention time of the analyte in the column. So property of the detector depends on what type of detector it is. So if I have here, let's say a UV detector, then it is going to display more like an absorbance of the samples or the various components against the retention times of the analyte. If I have something like refractometer, it is going to display the refractive indices of the samples against the retention time. So the retention times are how long the sample keep in the column, or we can say retention time is the time difference between the injection period and the ejection period. That is how long the analyte kept in the column. Now this peaks which is displayed on the chromatogram corresponds to the samples in the column. So as when we take a TLC, the number of spots displayed on the TLC depicts how many components are in that mixture. The number of peaks that are displayed in the chromatogram of HPLC also corresponds to how many components are in that mixture. So when I take this one as a chromatographic system or chromatogram, I have peaks, let's say 1, 2, 3, 4, 5. So 5 peaks mean that the sample that I introduced into the system contained 5 different components. Some peaks or some chromatogram displays a small peak in front we call the dead time. The dead time. So the dead time is different from the analyte peaks. So if I have this particular peak, which are 5, this peaks means that I have just 5 different components of the mixture or in that particular mixture. Now, the values that each of them will display on the x-axis are what we call the retention times of the analyte. So when I take, let's say, my peak A, its corresponding value on the x-axis. So if I'm to trace this, the difference between here is 8, here is 16. Let's say when I trace this one down, the A peaks has a value on the x-axis that let's assume is 14. That value here becomes the retention time of the particular peak A. When I take this particular unknown peak, which corresponds to an unknown sample too, when I trace it's down here, the x-axis, then the value here, which let's say maybe is roughly maybe 10, that value corresponds to the retention time of that analyte. And the retention time is basically how long the analyte keeps in the column. So if you are dealing with, let's say, a normal phase HPLC, where we have a highly polar silica gel, the analyte which tends to have the highest retention time is going to be the most polar because it is going to retain long in that particular column. In other words, the one which has the least retention time will have the least polarity among the sample. But if you are dealing with a reverse phase, then the process is reversed. So for a polar system or for the polar stationary phase, the analyte with the highest retention time is the most polar. About a non-polar stationary phase like the reverse one where we have, let's say, carbon 18, the analyte which comes out very fast rather tends to be the most polar, or the analyte which tends to have the smallest retention time is the most polar in the reverse phase system. So take note. Now the next thing we're going to look at is what we call the band broadening. Band broadening. So when we take every chromatographic system, the analyte runs through the column as shown here. So when they move through this column from this end to that end, they are going to be separated into layers or bands. And this separation is basically based on the ability of the analyte to have differential affinity with the adsorbent material. So as they move, they can divide into layers or they fractionate, and each fraction is what we call a band in a chromatographic system. And this band can be narrow or it can be broad based on several parameters or based on some precautions that you undertake in the chromatographic system. Now when we say band broadening, it is basically the diffusion or the expansion of the various components of the analyte as they run through the chromatographic system. So this shown here is basically what happens in the column. Let's say I start with my analyte at this particular part. Here is where I introduce my analyte in the column. And this mixture is made of two components, which I have labeled here as, let's say, green and red. Now, as they move down the column, separation is going to begin. So at a particular step A, the two are mixed together. Then at step B, which is also in the column, separation begins to appear. So the red one will now start to emerge from the green one from the mixture. Then at step C, which is also still in the column at time C, what is going to happen is now I see a proper resolved peaks for each of the analytes compared to B. Now let's say at step D, here's where there is proper resolution. That is, there has been a measurable distance between the two peaks in the chromatographic system. So as they move down the column, this is what happens. If I have the analytes having two different affinities, then they are going to separate, sequentially when they move. Now with this, if I have something like let's say I have a normal phase HPLC system, when they move down, if this one, the movement is down a column, then I will say that the one which moved very fast from the column will have, let's say, less affinity, or is going to be less polar compared to the one which moved slowly down the column. So these bands or these peaks, as they move here, it appears very narrow, but when they move down, they tend to expand. They tend to expand. So if this is my analyte that I added in the column, if this is my analyte, then I can say that when the particular analyte is very narrow, it appears very narrow, or it will have a very narrow peak. But as it moves down the column, there is where diffusion or expansion of the analyte occurs, and the analytes will have a broader band. Now, if the band of the analyte in the column is very broad, then its peaks too will tend to have a very broad peak. Now, the base difference between the peak for each analyte is what they call the width, or the base width. So when I take this particular peak like this, the distance between here, this part, and that part is what I call the width of the peak. If the band for the analyte is very broad, then it will have a very wider width. The width is very wide. So basically, if the band is broad, then the peak tends to have a very broad width. The resolution tends to be very poor. So when we say resolution, that is the measure of separation between two peaks. For a broader band, it tends to have a very poor resolution. If I have two peaks, let's say A and B, and I want to find the resolution between the two peaks, I'm going to use this expression, which is 2 times the difference in the retention times of the two divided by the addition or summation of the width of the two. This value is what I'm going to use to determine or predict the resolution that exists between the two peaks. For broader bands, if they are together, they tend to have a very poor resolution, but if the bands are very narrow, they tend to have a very proper resolution. Now, what factors account for the broadening of the band in an HPLC chromatographic system is what we are going to look at in the subsequent slides. Let's talk about column efficiency. When we say column efficiency, the ability of the particular chromatographic column to resist band broadening, or to ensure proper separation, or to ensure good resolution between two peaks or two components of an analyte is what is meant by column efficiency. If a column is efficient, then we say it is going to be very proper in terms of separation. It is going to have good separation between two different analytes or two different components in a mixture. Now, for a chromatography system, there is this idea that we have to know under chromatography. If I add my analyte to, let's say, this the column, then I add the analyte at this particular distance, or this particular region, and it moves down the column. The separation is basically based on the differential affinities of the analytes to the adsorbent particle, that is the adsorbent. Now, what enables the separation between the analyte or of the analyte, or how the separation occurs is basically if the analyte is going to be distributed differently between the mobile phase and the stationary phase. So when I take an analyte, let's say my analyte A, I introduce it at the beginning of the column. As it moves down the system, there is going to be a differential equilibration of the analyte between the mobile phase and the stationary phase. So it is more like the analyte is going to be absorbed to the adsorbent and get dissolved to the solvent phase, adsorbed to the adsorbent and get dissolved back to the solvent phase, adsorbed like that. So this adsorption and the desorption of the analyte between the mobile phase and the stationary phase is what enables the separation of the analytes down the chromatographic column. It means that for every particular analyte, since the polarity of the silica gel or the adsorbent particle in the column is constant, there is always this discrete distance in which the analyte is equilibrated between the mobile phase and the stationary phase. And when I say equilibrated, it's more like the analyte is being absorbed by the stationary phase and get dissolved to the mobile phase. So this mechanism of absorption and adsorption occurs at a very discrete distance for each particular analyte. So for every analyte, it has its own discrete distance which is constant, in which the analyte itself is absorbed and dissolved within the chromatographic column. And these discrete distances in which the analyte, they are just imaginary. So we say they are imaginary. So these imagined distances in which the analyte is absorbed or dissolved between the mobile phase and the stationary phase, or in which the analyte is equilibrated, is what we call the theoretical plate. So for every system or the column, we say it is full of theoretical plates, and these plates are just some discrete or imaginary distances in which the analyte that you introduce to the column is being equilibrated between the mobile phase and the stationary phase. Now there is this expression when we say the n. This n here is what we mean by the theoretical plate. So as we see here, so the n here, theoretical plate, which represents the discrete distances within the chromatographic column in which the analyte is absorbed and dissolved within the or between the mobile phase and the stationary phase. Now the number of theoretical plates, I said, is constant for every particular analyte in the column, and is given by this expression where the TR represents the retention time of that particular analyte, or it can be related to the length of the column in this expression. So the number of theoretical plates we term as the n, we say it is equal to the length. The L here is the length of the column. Then the H here represents the height of the theoretical plate. So the discrete distances in the column are what we call the theoretical plate. The N represents the number of those theoretical plates in the column, and the H represents the height of these theoretical plates. So when I take this expression, N equals L over H, the N represents how many theoretical plates I have in the column. The L represents the length of the column. Then the H represents the height equivalent of the theoretical plate. Now for every chromatographic column, there is this assumed, idea that the number of equilibrations between the mobile phase and the stationary phase for the analyte increase or improves the column efficiency. That is to say that if the number of theoretical plates of a column for an analyte is greater than the column, we say it is more efficient. So the number of theoretical plates n is proportional to the efficiency of the column, which let me say I'll represent by E. That means if you increase the number of theoretical plates, then the efficiency of the column is going to also increase. At the same time, if the L, which is the length of the column, also gets increased, then the efficiency tends to be high. Now, if the H represents the height equivalent of the theoretical plate, if the H is rather decreased, that is where the N tends to increase and the efficiency would increases. So from this expression, I can say that as I increase N, efficiency increases. As I increase the length of the column, efficiency increases. Then as I decrease the H, efficiency would also increase. So it means that for me to have a more efficient separation, the H, which is the height of these discrete distances or the height of these theoretical plates, must be decreased so that I can have a proper efficiency of the column. So the N can be given by this expression, either this or that. I can find particular N, which is the number of theoretical plates for a particular analyte in a chromatograph. Using this expression, if I have the full width of that particular peak, or I can use this one if I can only detect half of the width of that particular peak. So as I said earlier, if the number of theoretical plates are greater, then the column is more efficient. Efficiency means that it ensures proper separation, it ensures good resolution, and it prevents overlap of the peaks in the chromatographic system. Let's come to what causes the bond or the band broadening. The band broadening. So if a band is able to broaden like this, as I said, it will lead to poor separation because one peak if I have this particular peak closer to another one that has nearly the same polarity, those two peaks are going to overlap. And when they overlap, I will say that what there is a poor separation or there's a poor resolution. That means for me to even be able to separate two different analytes that have close polarity, they have to get a narrow peak so that the peak of one will not overlap on the other. So what causes the band broadening or the broadening of the band are just the factors which are incorporated by an equation called the Van Deemter's equation. So the Van Deemter's equation are full of parameters or factors that account toward band broadening. So from what we said earlier in the H, with the H we call the height equivalent of theoretical plate, we said that for every chromatographic system, for you to ensure good separation or for you to ensure proper column efficiency, this H must be decreased. So anything that can increase this value of H can be a disorder, or let's say a limitation to chromatographic separation. Now Van Diemen's equation incorporates these three factors called factor A, B, and C. These factors try to explain how or what causes diffusion of the analytes in the chromatograph system. And when the analytes diffuse or spread out in the chromatograph system, it tends to increase the factor H. And when factor H increases from this expression, we can say that when we have an increased H, there is going to be a reduced efficiency of the column separation. So for me to enhance proper column efficiency, the factor here must be smaller. So for the H to be smaller from the Van Diemen's equation, factor A, B, and C in the Van Diemen's equation must be smaller or must be diminished so that the H2 must be smaller. If the H becomes smaller, that's where efficiency of the column tends to improve. Now these factors A, B, and C, what are they? The A in the Van Diemen's equation are what we call the eddy diffusion. The B is what we call the molecular diffusion or longitudinal diffusion. Then the C is what we call the mass transfer between the mobile phase and the stationary phase. So we are going to just elaborate on how each of these can cause diffusion or broadening of band in a chromatographic system and how it can be minimized. The mu or the U here is what we call the linear flow rate of the solvent or the solvent flow rate. The first factor of the Van Diemen's equation is the eddy diffusion. Now, how do this eddy diffusion factor A causes band broadening or spread of the analyte in the column? So let's think about this. Let's say I have this particular analyte with this peak at the beginning has very narrow peak. Now these analytes have atoms in it, so several atoms of the same compound. When they start running from the beginning of the chromatographic column, it tends to be narrow because we see the two of them are at the same place, and when they are at the same place, they will all be detected at the same time. Now, what will happen when the analytes move down the column? These atoms that are represented as, let's say, green and red, they take different paths down the column. So when they take different paths down the column, what is going to happen is the one that took a very shorter path through the column will reach the detector at a very faster rate. Then the one that took a very longer path in the column will now reach the detector at a longer rate. That means that if I have several atoms of that compound in the green direction, then several of that atom in the red direction, all those that took the path of the green will now get the detector before the ones that took the red direction. So when they get to the detector at different times, they are going to enhance or broaden the peak. So when the red, let's say the green gets here, is at this particular place, then the red, since it took a very long path, will now be moving here. Now, since these two are of the same compound, it means I'm going to have a spread of the atoms of the analytes in this particular region. So when they spread like this, then I can see that what the band for that particular analyte has broadened. Now, when the band broadens, then the peak also becomes wider. If we have such case, then I'm having more than one component or compound. If one broaden like another one also broaden in that same manner, then the peak of one will overlap on the other, and that leads to what? A very poor resolution. So the factor A we call the diffusion is basically diffusion caused by multiple paths that is being traveled by the analyte down the chromatographic column, and that leads to a broadening of the chromatographic peak. That's for the factor A. The next one is factor B. Factor B we call the longitudinal diffusion. So if the analyte itself they move down the column, let me even come back to the factor A. So what will cause multiple paths in the chromatographic column? So what increases factor A is if the particle sizes are not even. So if you have an uneven particle sizes, it creates different path in the column. And when that creates different path in the column, it leads to different directions being taken by the same atom of the atom of the analyte in the column. If I have different path being taken due to the fact that what I have an uneven particle sizes, then I'm going to cause eddy diffusion. Or if I have non-uniform packing, if even the particle size are even, but I have non-uniform packing, the analytes or the atoms of the same compound will travel through different paths and get to the detector at different times. So when you get to it at different times, it will lead to what? A broadening of the peak or a broadening of the band. So what causes factor A to occur is an increase or a non-uniform particle sizes or non-uniform packing. So if particle size some are big, some are small, it will create different paths in the column. Bear in mind, this factor is not dependent on the solvent flow rate, because even if you increase or decrease the solvent flow rate, it will still create or it will still allow the multiple paths to occur in the column. So first we have non-even particle size or non-uniform packing. Factor B is what called the longitudinal diffusion. So this one is just the natural diffusion which will occur in the analyte. If the analyte tends to keep long in the column, sometimes if it keeps long in the column, the atoms of the analyte itself will now spread in what the longitudinal direction. One will go up, one will come down. If I start here, this particular band, and as it moves down the column, the movement is so slow because of the diffusion. The light here will now travel from the region of higher concentration to the region of lower concentration. That is if the motion or the movement of the analyte here is too slow in the case of low solvent flow rate. So when there is increase in the band like this down the column, the peak becomes broadened. So this one is for the beginning where the peak is narrow because it is not that diffused. As it moves down the column, then the spreading comes. Now, when it gets to where the detector is, it will become very wider. It widens because it has diffused longitudinally. So when it diffuses, then the band or the peaks broaden. Bear in mind, if the peak broadens, it leads to poor resolution between two adjacent peaks. If I have this particular peak and another one which is very close to it, that one may overlap on this one because this one has what? Spreading. If this one is made much better, maybe at the beginning it will look like this for different peak, but when it widens, it will now overlap on the new peak, and this will lead to poor resolution. So that is for the longitudinal diffusion, for just longitudinal movement or expansion of the analyte. Bear in mind, this factor is dependent on the solvent flow rate. This diffusion occurs only when the analytes keep long in a column. So when it keeps long, there is a diffusion longitudinally can occur. So the solution to this particular, expansion or this particular disorder is what? If you increase the solvent flow rate, you can minimize the time the analyte spends in the column, and that can lead to a minimized longitudinal diffusion, or it can lead to what? A narrow peak instead of what? A broad peak. The last one is what we call the mass transfer coefficient or the mass transfer. So if I have this particular analytes here, they move down the column, and let's say the silica gel or the packing material in the column are also not even, there is going to be resistance of the analytes. So as they move down the column, If the particle sizes are not even, it is going to resist the movement of some whilst it frees the other to go in. So when they move here, this at the beginning, we have the zero flow because let's say there is a resistance. As they move down the column, the ones that the particle or the packing material blocked will now be resisted from movement. Then the ones that had their way through will now move slowly. So at the time they get to the detector end, what will happen is the one that got blocked will still be delayed. Then the one that didn't get blocked will now get the detector. So whilst the unblocked ones will get here, the blocked one will now be moving here because they got resisted by the silica gel. In that case, you will have a broadening of the band. If the band broadens, it will lead to a very wider peak in the chromatographic system. In all cases, if the factor C increases, it will increase the value for the H. And if the H, which is the height, increases, the column C becomes less efficient. So from what we have discussed so far, we can say that from this Van Deemter's equation, for us to have a minimal value for H, the A value must decrease, the B must decrease, and the C must decrease. If A, B, C, all these values get decreased, that's where the number of theoretical plates will get increased. And if the number of theoretical plates get increased for a particular column, the column is more efficient. That means every correction that you put in place to correct any of these can help minimize the value for the height of the theoretical plate. So for the A, we say the A is independent of the solvent flow rate. So the only way you can correct A that is caused by multiple paths that the analyte take is to ensure uniform packing or ensure even particle sizes. The next one is B. So this B, since the B is dependent on the solvent flow rate, if I want the B value to be very small, or that if I want to prevent longitudinal diffusion, then I have to increase the solvent flow rate. So if I have a very small flow rate in the column, the B factor tends to be very large, and that will lead to an increased value for H, leading to poor column efficiency. So correction for B is you have to increase the solvent flow rate. When you increase the solvent flow rate, the B factor will tend to decrease. That is, you tend to minimize longitudinal diffusion. Now, when that diffusion is minimized, the factor H also would get minimized, and it leads to an improved column efficiency. The last one is C. So this C is dependent directly on the solvent flow rate. So if you increase the solvent flow rate, it will also increase with the C, because the C is resistance to mass transfer. If you increase the flow rate, the one that got blocked will still be delayed, but the one that passed through will now move at faster rate. So for a chromatograph system, if you increase the solvent flow rate, the C factor will tend to increase, but the B will decrease. At the same time, if you decrease the solvent flow rate, the B factor will increase, then the C will decrease. So no matter what you do, the B and the C one of them will be affected. That means that you have to use a flow rate that is optimal to all of them. So you have to use an optimal flow rate. An optimal flow rate. And an optimal flow rate is given by the ratio of the square root of B to C. That is optimal flow rate. That favors both B and the C. So this curve here is called the Van Deemter's curve, which is a plot of the height of the theoretical plate against the flow rate. So for what you have here from this expression, if the factor A contributes to the H at this particular value of H, when you increase the flow rate, the A value remains constant because the A is independent on the flow rate. The factor B, if it begins at this particular side, because it always tends to, diffusion always begins when you start a run, and you increase the flow rate, the factor B will decrease. That's why we say the B is dependent on the flow rate. So if you increase the flow rate, the B will also decrease. Then the factor C, since it has direct proportionality, if you increase the flow rate in this direction, then the C also increase at the same rate. So with all of them, when you blend all of them together, the resulting curve, which we represent here as this one, is the H, we call the height equivalent of theoretical plates. So this is the Van Deemter's curve, or the Van Deemter's equation, which explains the dependency of the height equivalent of theoretical plates on the edge diffusion, longitudinal diffusion, and resistance to mass transfer, or the mass transfer coefficient between the mobile phase and the stationary phase. Thanks for watching. Don't forget to like and share after watching so you can receive every bit of updates from this channel. Thank you.